Now, we've been talking a lot about the sun, and we've been working on the sun. We've learned a lot about other stars, and the reason we need to know about those other stars is because our sun is a star. They hold some key information that we might need in other stars, so we study them to help us understand our sun. Now, today I may go over some things that are a review, but I want you to make sure you take really good notes while we talk. I want to start with properties of the sun. The sun is 330,000 times the size of the earth in diameter. The sun is extremely large, and this is very important to some of the abilities of our solar system. The sun's interior is made up of a gas. We really need to focus on that here shortly. That is a major key to our sun. The sun's surface, the sun's core temperature is 10 million degrees Kelvin. That is extremely hot. For example, Kelvin is a scale that starts at absolute zero. That at that point, all motion stops. When we look at Kelvin temperatures, it's 237 degrees plus our Celsius number for a legitimate reading for us to understand. For example, if water freezes at 0 degrees Celsius, that'd be 273 degrees Kelvin. The sun's surface produces huge amounts of energy, specifically energy that we can harness to make light energy. If we were to try to light bulbs on the sun's surface, we could light 4 trillion trillion, that's 4 trillion trillions of light bulbs. That's a large number. It's very difficult for even me to wrap my brain around 4 trillion trillions. That's 4 trillion worth of trillions of light bulbs. Now, the very interesting thing with that is not all that energy makes it to the earth. Very, very little of that energy makes it to the earth. Only 1.35 kilowatts of energy make it to the earth's surface. Most of it's absorbed throughout the atmosphere and in small particles in space. Something major to remember is the sun does have layers, and you've spent quite a bit of time analyzing those layers in your vocabulary. The sun also produces huge amounts of energy. It produces this energy through reactions known as fusion and fission. Fusion is the putting together, or fusion is the putting together of particles. Fission is the splitting of particles. This actually creates a growing and shrinking aspect to it, and as particles are put together, the core of the sun or star will actually start to get heavier and even in some cases change its elemental structure. Much of the sun's energy is absorbed through our atmosphere before it gets here. That's very important about the energy of the sun. Our atmosphere absorbs large portions of it before it reaches the actual surface of the earth. Have you ever wondered if you get sunburned differently in different locations? I travel all over the United States, and that does occur to us every once in a while. If you're high in the mountains, you get worse sunburns because you're closer to the sun. Down here to Alabama, we get sunburns because it's on the equator, and we spend a lot of time in the sun. As we move to star evolution, evolution means change. Stars change. Some of the major points of how stars change go to lead for us to understand the life of a star, and in turn the life of our sun. Stars change due to nuclear fusion, changing elements that construct the star's inner core over time. Our sun is created from hydrogen, and it fuses hydrogen to make helium. Over time, this will change the elemental structure of our sun. As stars get older, its density increases and its brightness increases, meaning that over time our sun will get brighter. All stars get brighter as they age. At some point, its core will solidify, and that will drastically change its gravitational pull. It will not solidify, though, until it's changed all its hydrogen to helium, and then all its helium into carbon. After a formation of a star, the first cycle of life of a star begins. Now, that formation is when all these particles of basically space dust crash in on themselves in gravity, create this huge source of heat, vaporize all of it, and begin a perpetuation of a fusion reaction, creating this major ball of energy that self-propagates larger and larger and larger until it gets to whatever point it is in its solar system. This first cycle, though, lasts for 10 billion years. 10 billion years. Now, it's an estimate. We weren't there when the sun started, so did we start counting time? No. The Earth is roughly 4.6 billion years old, and so if the Earth was created near the same time as the sun's probably in a 5 billion year or 6 billion year cycle at this point in time, and there's 4 billion years left on its life term. As the cycle continues, the star moves in one of two directions. It either continues into what's called a red giant or a white dwarf. If it is small, and the cycle moves to a white dwarf star. If it is a large, it moves into a red giant. Our sun will move into what's called a white dwarf star. Now, this concludes our discussion on the evolution of a star. I'm going to attach some material that I've collected out of our textbook that I do really want you to read and go through. Later on, not today, not tomorrow, but I will have you write a model, a written model, of what you believe will happen to our sun and why. You will need that material and these notes to be able to complete that portion of our assessment. By Friday, we may be ready for a test. I would make sure that I have taken good notes and filled out the outline that I will be attaching to this shortly, completed our vocabulary, and the activity of Monday, answering those review questions. If you have any questions, please email me, get in touch with me, and I will help you out as much as possible. We will finish this up, hopefully by Friday. Have a great day.